Hello everyone. Today we are going to talk about pipeline, data paths, and control. We are going to use the 5 instruction sequence as an example. We assume that the program counter is 5,000, 1,000, and register 1 is 1,000, and so on. So first of all, the load word instruction is getting into the pipeline architecture. So it is in the instruction fetch cycle. This is a clock number 1. And of course, the program counter is 5,000, 1,000, and it is reading the instruction memory to get the value instruction, which is AC290014. So that's the load word instruction 32-bit encoding. And at the top, what happened is that the program counter value is added with the by 4, so it produces the 5004, and the value is actually ready to update the program counter. But during the 1 clock cycle, before the rising edge of the cycle, rising edge of the cycle 2, all the values are ready to get updated. And what happened is that at the rising edge of the clock, the value on the left-hand side is finally update the value, for example, program counter. So program counter now becomes 5004, and the value, before the IFID pipeline stage, which was the 32-bit instruction for load word instruction, AC2A0014, is finally moved to the ID stage. So now using that value, ID stage is actually executing on behalf of load word instruction, and at the same time, the subtract instruction is entering the IF stage in the pipeline architecture. So in the ID stage, load word instruction RS is, instruction is decoded. So the RS is 1 and RT is 10, and register is being read. So the value of register 1 is produced, the value of register 10 is produced, and 16-bit offset in this case is 0014. So that is extended to 32-bit. And one important thing is that the destination register for load word instruction is 10. But in the ID stage, it's not actually used. So you have to carry over to the next stage until the load word instruction is in the write back stage. At that time, we need to know that what is the destination register number, which is 10. So we need to carry over until the write back stage is reached. So in cycle 3, load word instruction is getting into the execution stage. So again, at the rising edge of cycle, beginning of the cycle 3, at the rising edge, all the values on the left-hand side is a carry over to the right-hand side. So now all the execution stages, all the signal lines will carry the values relevant to the load word instruction. And so the ALU is performing computing the memory address for load word instruction. We get the value of 0014, which is the second source of the ALU, and the first source of the ALU is register 1 content, and ALU is computing the memory address. And at the bottom, the value of 10, which is the destination register number for load word instruction, is still, the carry at the bottom. In cycle number 4, the load word instruction is in memory stage, and it is actually reading the memory data. And at the same time, the destination register number 10 is still carryover at the bottom. And in the execution stage, the subtract instruction is computing the register 2 plus register 3, and it also carries its own destination register number 11, from stage to stage. In cycle 5, finally load word instruction moved to the write back stage, And at that point, we get the value from the memory, which is going to be written to the destination register number 10. And as you can see, number 10 from write back stage is kind of a feedback to the register file. At the same time, write data is also feedback from write back stage to the ID stage to finally update the destination register 10. So, that is the reason why we have to carry the destination register number from stage to stage until it is actually utilized. And also this five figures tells you that the instruction is moving from one stage to the next stage in the pipeline architecture. So until we talk about the pipeline data path, and now we are talking about pipeline control, such as register destination control signal, ALU/SRC, and MAM2 register control signal, and so on. So for example, addition instruction and a load word instruction is executed same time in the pipeline architecture. Regarding the addition instruction, register dest must be 1. On the other hand, load word instruction, register destination must be 0. So, there is a confusion. So what we, our implementation is that we generate the control signal all at once at the ID stage, and we pass them through stages like all the data we, pass through stages. So if you look at the figure at the bottom, in the ID stage, based on the OP code, the same control, the circuit is producing 9 control signal, and it is producing, those 9 control signals are the pass to the execution stage, and some of the control signal are used in the execution stage, so those signals you don't have to carry again. On the other hand, some other control signal must carry over to the memory stage and then the write back stage until it becomes used. So, among those 9 control signals, we need to categorize them into those that are used in the write back stage, those that are used in memory stage, those that are used in execution stage. So this table shows that those 9 control signal in in those 3 different categories. So RDJ DSD, ALU OP1, OP0, ALU SRC, they are used in execution stage and so on. So here is more like the overall diagram of the pipeline architecture, including the control circuit. If you look at the rightmost side, at the write back stage, we only need the 2 control signal, which is a register write and MAM2 register. So that particular control signal are in fact generated in ID stage, but it is a carryover to the execution, memory, and write back stage. And when the instruction is finally in write back stage, that control signal is finally utilized to control the operation. So just to give you an idea how the those control signal works with the 5 instruction sequence. Let us say load word instruction is coming into the instruction fetch stage. In clock cycle 2, it is moving into the ID stage. At that point, 9 control signal will be generated based on the control circuit, and in the cycle number 3, load word instruction moving into the execution stage at the same time. Those 9 control signal also carry over to the execution stage, and of course some of them are used in the execution stage, but other 5 control signal is just simply passed to the next stage, which is MEM stage. So the just about the same the same explanation that like all the other data signals, the control signal are also the pass through the stages to stages until they are used. So section 4.7 is a data hazard issue, and basically the hazard is the important concept in pipeline architecture. We'll discuss a little bit more detail, but at this point, we just focus on data hazard. So needed data still being computed by previous instruction. For example, in this instruction sequence, the subtract instruction, register 11 is the destination, and the following instruction and the instruction, register 11 is one of the source register. And what happened is that subtract instruction, IF, ID, EX, MEM, WB. So according to our structure, the updated value, the new value of register 11 is getting updated in cycle 5 in write back stage. On the other hand, for this, with respect to AND instruction, it is reading the two source register during the ID stage at cycle 3. So we need the updated value of register 11 at cycle 3, but the updated value of register 11 is only available at cycle 5. So I mean, so time-wise, it doesn't work. So only possibility is that we have to stop the pipeline, restore the pipeline to cycle. And luckily, the write back stage, we are updating the register 11 at the first half of the cycle, and the reading ID stage is done during the later half of the cycle. If you remember, the previous lecture. So we can actually the write back into register 11 at cycle 5, and it is also possible to keep the value to the newer value of register 11 in cycle 5 in ID stage on behalf of AND instruction. So anyway, we just but we still need to stop the cycle, the pipeline 2 cycles on behalf of AND instruction, and this is called the data hazard. And because it is a pipeline hazard, but it is because it is happening because of the data conflict. So the hazard in general is defined as when an instruction's stage is unable to execute during the current cycle, and the possible, easiest the solution is to stall or delay the pipeline. But the thing is, when the instruction 2 is stalled one cycle, the following instruction has to be stalled as well because of the resource conflict. So this is a pipeline hazard. And there are 3 types of pipeline hazard: structural hazard, control hazard, data hazard. Well, data hazard, we already saw that source data not yet available, such as register 11. And control hazard has something to do with the branch instruction. And structural hazard is somewhat related to resource conflict. The structural hazard may be easier to solve because, if we need the one more ALU, if there is a resource conflict for the ALU, well, we can just have one more ALU in the architecture. So as long as we have enough resources, structural hazard might be easier to solve. On the other hand, the control hazard and data hazard are relatively more difficult to solve. So in the next time, we'll discuss more detail about those 2 hazards, data hazard and control hazard. Thank you.